Hello, welcome back to AC Circuit Analysis. We have kind of a simpler problem, but what we were asked to find, we're given this circuit here, and we're asked to find the average power, the reactive power, and the complex power absorbed by the load. The load is everything inside the dotted line, so these two elements here. Now notice though that we're given our source is a current source, but it's given in the time domain, right? And our inductor is given in henries and our capacitor is given in microfarads, so we have to do a little bit of work here to get anywhere, essentially. But the game plan essentially is going to be, we're going to make this into a phasor, then we're going to use the frequency here, which we're given in the problem, wrapped up in the cosine, to find the impedance of this inductor, the impedance of this capacitor. Then we're going to use some sort of circuit analysis to figure out what the current is flowing through here. I mean, there's different ways to do it. That's what I'm going to do. And once we know that, we can find complex power, magnitude I squared times Z, the impedance. And so once we have S, the complex power, then we can just read off the average and the reactive power. So you see the problem looks like it's asking for a lot, saying average power, reactive power, and complex power. But really, once you have the complex power, these other things are really written down on the page. So the first thing we need to do is crawl before we can walk. We need to take a look at the source. It's 30 times the cosine of 100t, but it's given in milliamps. So the source is really the following. It's really 30 times 10 to the minus 3 at an angle of 0 degrees, and that would be amps, because this is given to you in milliamps. So typically what you want to do, you don't have to do this if you can keep it all straight, but typically what I do is I convert everything back to amps, or our base units. If I'm given millivolts, I work in volts and things like that. If I'm given milliohms or kiloohms or whatever, I work in ohms, and I get the answer, and then if I need to convert units back, that's what I do. And that way I never have to keep track of, oh, this was a milliamp and that was a kiloohm, so what do I do? I never have to worry about that. I go back to my base units. So when you look at this 30 times 10 to the minus 3, to simplify it, it's just 0.03 at an angle of 0 degrees, and that's going to be in terms of amps. So that's what the source is. Now notice also that the angular frequency is given to us in the problem because it's right in, whatever's written right in front of the time. So it's 100 radians per second. Usually we don't care about that because these are linear circuits and the frequency is going to be what the frequency is going to be, but we need it in this case because we need to calculate the impedance of some of these guys, and we'll need to know the frequency for that. So let's go ahead and do that right under here. So we're going to calculate the impedance, let me change colors real quick, the impedance of the inductor, Z sub L. This is not Z sub load, this is just Z sub L, the inductance of, or the impedance of that 10 Henry inductor there. What is the impedance of an inductor? It's J omega L. So in this case, it's J times 100, omega is 100, times L, which is just 10. All right, so the impedance of the inductance written there in the circuit there is just 1,000, J 1,000 ohms. All right, so I'm going to mark that on the problem here. Now we know that, I'll write that down as J 1,000 ohms. Don't get confused, I'm just writing it down there so that we can reference it as we go on. Now, let's go ahead and calculate the impedance of the capacitance, Z sub C. What is the impedance of a capacitor? It's 1 over J omega times C. That's how I remember it anyway. You might remember it slightly differently. There's a couple different ways to write it. J omega is 100 radians per second. The capacitance is 2 microfarads. So when you do this calculation, you need to write 2 times 10 to the minus 6, and then bring your fraction bar over so you make sure you do everything correctly. And when you put that in your calculator, 100 times the 2 times 10 to the minus 6 times J, and then you take the inverse of